So you want to own a semiconductor factory. Picture it for a second. A building the size of dozens of football fields. Robots gliding silently through hallways of glass and steel. Scientists in full-body suits handling machines more precise than anything else humans have ever built. Somewhere inside, a piece of silicon smaller than your fingernail is being transformed into the most valuable object on the planet, gram for gram. Everything from your phone to your car, to the AI running in the background of your life, traces back to a place like this. One of these factories can cost more than an aircraft carrier. It can take 5 years just to get from an empty field to a single working chip. A speck of dust invisible to the human eye can destroy millions of dollars of product in a single afternoon. And even after you've spent tens of billions of dollars and waited half a decade, there's still no guarantee the world will want enough of what you're making to ever pay it back. This isn't a story about engineering. This is a story about money. The strangest, most extreme, most unforgiving version of capitalism that exists anywhere on Earth. Today, we're going inside the real economics of owning a semiconductor factory. Let's start with the question almost nobody asks correctly. What are you actually buying? Most people think a semiconductor factory, engineers call it a fab, is just a big building full of machines. But that's not really what you're buying. You're buying physics. You're buying chemistry. You're buying decades of accumulated knowledge about how to manipulate matter at a scale smaller than a virus. You're buying a supply chain that stretches across a dozen countries, a workforce of specialists that took years to train, and a level of precision so extreme that a single misplaced atom can ruin an entire product. Inside these buildings are rooms called clean rooms, spaces thousands of times cleaner than a hospital operating theater. The air is filtered so aggressively that a single speck of dust, something you'd never even notice on a table, is actually larger than some of the features being carved into these chips. Workers don't just wear masks, they wear full sealed suits, because a stray eyelash or a flake of skin can wreck a product worth thousands of dollars before anyone even notices. That already sounds expensive. It gets worse, because here's what surprises almost everyone the first time they see the real numbers. People assume a factory like this costs a few $100 million, a serious investment, but a normal one. The reality is almost incomprehensible. A modern, cutting-edge semiconductor fab can cost $10 billion. Many cost 20. The most advanced ones on Earth today are pushing past 30, even $40 billion. For a single facility. Where does all of that money actually go? Land and construction are only the beginning. You need staggering amounts of electrical infrastructure, because these factories consume power on the scale of a small city. You need water treatment systems capable of producing water purer than anything used in medicine, because a single mineral particle in the wrong place can ruin a wafer. You need automation systems, robotics, testing equipment, research labs, and packaging lines. And here's the twist that changes everything. The building itself, as massive as it is not even the most expensive part. The machines are. This is where the story shifts from impressive to almost unbelievable. Inside these factories sits a single category of machine so advanced, so absurdly difficult to manufacture, that only one company on the entire planet is capable of building it. It's called an EUV lithography machine, and its job is to use light to carve patterns onto silicon that are smaller than a strand of DNA. A single one of these machines can cost more than $100 million. Some configurations cost several $100 million, and a factory doesn't need just one, it needs dozens. These machines don't simply get bought and installed like office equipment. They arrive in pieces, packed across dozens of cargo containers, requiring specialized aircraft and convoys just to transport. Installing a single unit can take months, with teams of engineers flying in from around the world to assemble it piece by piece inside the clean room. And here's the hidden truth that most people never consider. Without this one machine, the entire multi-billion-dollar factory around it is nearly worthless. All that steel, all that glass, all that infrastructure, it exists purely to support a handful of devices that can individually cost more than a fleet of private jets. Which raises an obvious question. If the machines are that expensive, why doesn't every wealthy company just buy a few and get into the business? Because money was never really the barrier. Knowledge is. Building a semiconductor factory requires assembling one of the rarest concentrations of specialized expertise in human history. You need physicists who understand how light behaves at scales smaller than atoms. You need chemical engineers who can design processes involving hundreds of different gases and chemicals, many of them toxic, some of them explosive if mishandled. You need software engineers capable of controlling systems with zero tolerance for error. You need a global network of suppliers, each one mastering a single ingredient in a process with thousands of steps. Hundreds of companies, spread across dozens of countries, all have to get their piece exactly right, every single time, for one chip to exist. Add government approvals, export regulations, and intellectual property law, and you start to understand why there are only a handful of companies on the planet that can actually pull this off. Not because nobody has the money, but because almost nobody has all the pieces at once. And even once you've built the factory, hired the experts, and installed the machines, here's where it gets interesting. You start losing money the moment you turn it on. This is the part almost nobody expects. Every machine inside that factory begins losing value from day one. Technology moves so fast in this industry that a machine considered cutting edge today can be functionally outdated within a few years. New generations of chips demand new processes, and factories that can't keep up become less competitive, almost in real time. In accounting terms, this is called depreciation, and in this industry, it isn't a footnote. It's one of the central forces shaping the entire business. But depreciation is just the beginning of the hidden costs. Here's what nobody sees when they picture a chip factory. Beyond the machines, you're paying for a staggering list of ongoing expenses, enormous quantities of electricity, oceans of ultra-pure water, specialty gases so rare that some of them are sourced from only a few locations on Earth, hazardous chemicals requiring careful handling and disposal, climate control systems running non-stop to maintain exact temperatures, security systems protecting trade secrets worth billions, insurance policies covering catastrophic risk, and software licenses for systems that control every micron of the manufacturing process. One factory alone can consume as much electricity as an entire small city, running 24 hours a day, 7 days a week, without ever fully stopping. Now here's the number that matters more than any of that. It's called yield, and it might be the single most important word in this entire industry. Here's the simple version. A factory doesn't make one chip at a time. It carves hundreds of tiny chips onto a single thin disk of silicon called a wafer. But not every chip on that wafer works. Some come out perfect. Some come out with microscopic flaws that make them useless. The percentage that actually work is called the yield, and in this business, tiny differences in that percentage translate into massive differences in profit. A yield of 95% instead of 90 might sound like a small difference, but multiplied across millions of chips, it can mean the difference between a hugely profitable quarter and a devastating loss. This is why entire teams of engineers spend their careers chasing fractions of a percentage point. In this industry, invisible defects are where billions of dollars quietly disappear. Which brings us to a strange economic truth. Bigger is almost always better here. This is where the economics completely change. Because these factories cost so much to build and run, regardless of how many chips they actually produce, the fixed costs are enormous, and the variable costs are relatively small. That means the more chips you can push through the line, the cheaper each individual chip becomes. Economists call this economies of scale, but in the chip industry, it becomes something even more extreme, something called operating leverage. Run the factory at full capacity, and profits can be enormous. Let it sit even partially idle, and the exact same fixed costs remain, quietly draining money every single day. An idle semiconductor factory doesn't pause its expenses. It still burns through millions of dollars a month, whether it's producing a single chip or not. And that leverage becomes even more dangerous when you consider the supply chain holding this entire system together. No single company, no single country controls everything a chip needs to exist. The raw silicon, the rare gases, the specialized chemicals, the copper, the packaging materials, the shipping routes, they're scattered across the globe, and if just one link breaks, production can stop everywhere at once. A pandemic can shut down a supplier on the other side of the world. An earthquake can knock out a single factory that happens to produce a component nobody else makes. A geopolitical conflict can instantly cut off access to a material an entire industry depends on. In an industry this specialized, dependence isn't a risk on the margins. It's baked into the foundation of the entire business. Which is exactly why, at this point, most people assume these factories are purely private ventures, built and owned entirely by corporations chasing profit. But that's not the full picture either, because these factories don't just produce chips, they produce power, national power. The country that controls advanced chip manufacturing controls the backbone of modern military technology, artificial intelligence, communications, and infrastructure. That's why governments around the world have started pouring enormous sums of money into subsidies, tax credits, and incentive programs just to convince companies to build these factories on their soil. Some of the most advanced factories on Earth today would never have been built without direct government funding. This isn't just an industry anymore. It's a matter of national security. So with all of this cost, all of this risk, how does anyone actually make money doing this? Here's where the business model splits in a way most people don't expect. Some companies design their own chips and also manufacture them entirely in-house. Others do something completely different. They never design a single chip of their own. Instead, they build factories purely to manufacture chips designed by other companies, under contract, for a fee. This second model is called a foundry, and it has become one of the most powerful business strategies in the entire industry because it means a single factory can serve dozens of different customers at once, spreading the astronomical fixed costs across an entire ecosystem of demand. Long-term contracts, guaranteed capacity commitments, and premium pricing for the most advanced technology are what allow these companies to slowly claw back the tens of billions of dollars they poured into the ground years earlier. But even the smartest business model in the world can't protect you from the next problem, and it's the one that keeps every semiconductor executive awake at night. Demand is almost impossible to predict years in advance, because that's the timeline you're working with. Decisions to build a new factory happen years before it ever produces a single chip. In that time, an entire industry can shift. A boom in artificial intelligence can send demand for advanced chips soaring far beyond anyone's expectations. A slowdown in smartphones or cars can leave factories producing chips nobody wants anymore. One mistaken forecast, made years in advance, can result in billions of dollars in losses, or billions of dollars in missed opportunity if you built too little instead of too much. And when a downturn actually arrives, that operating leverage we talked about earlier turns from a strength into a weapon pointed at your own balance sheet. Demand falls, but the machines keep depreciating. The employees still need paychecks. The debt used to build the factory still needs to be repaid. The electricity and water and chemicals keep flowing, whether the world wants your chips or not. Losing even 20% of demand can be enough to erase nearly all of a factory's profit for the year, because so much of the cost structure simply doesn't move. So why, knowing all of this, the staggering costs, the impossible complexity, the constant risk of demand swinging the wrong way, do investors and governments keep building these factories anyway? Because the prize, when you get it right, is almost unmatched. Technology leadership, long-term government support, market dominance in an industry that isn't going away, but accelerating. Pricing power over the most critical component in modern life. Strategic value that goes beyond quarterly earnings into the realm of national importance. Companies that successfully navigate this business don't just make money, they become nearly impossible to replace. Let's make all of this concrete with one hypothetical example so you can see exactly where every dollar goes. Imagine a company building a new advanced fab, construction and cleanroom infrastructure, $25 billion. Lithography and manufacturing equipment, $18 billion. Annual utility costs, including electricity, water, and specialty gases, $2 billion a year. A workforce of over 5,000 engineers, technicians, and support staff. Monthly production capacity of around 100,000 wafers, each containing hundreds of individual chips. In a strong year, with high demand and excellent yield, that factory can generate enormous profit, enough to start justifying the initial investment. But in a weak year, with softer demand and a dip in yield, the exact same factory, with the exact same costs, can swing to a painful loss. Same building, same machines, same workforce, completely different outcome, based almost entirely on forces outside the company's control. That's the real story hiding behind every microchip in the world. Most people imagine a semiconductor factory as something close to a machine that simply prints money, feed in raw silicon, receive endless profit. The truth is almost the opposite. It's one of the most capital-intensive, high-stakes businesses ever created by human beings. Its success depends on a combination of physics, chemistry, engineering, economics, global supply chains, government policy, and, ultimately, timing. The companies that survive in this business aren't necessarily the ones with the single best piece of technology. They're the ones that manage to balance innovation, capital, manufacturing precision, unpredictable global demand, and long-term strategy, all at once, for years on end, without a single catastrophic mistake. So the next time you pick up your phone, start your car, or ask an AI assistant a question, remember what's actually behind it. Somewhere in the world, inside a building that costs tens of billions of dollars to build, an invisible economic machine is still running, balancing on a knife's edge between extraordinary profit and staggering loss. one microscopic chip at a time.